Hello everyone, I'm Sebastian Y and this is Managerial Economics. In this video we're going to look at how to incorporate natural logarithmic functional forms into a regression. Up until this point, all the regressions that we have run have imposed a strictly linear relationship between variables. When x goes up by 1, y goes up by beta 1, no matter what the current value of x is. That relationship always stays constant. In reality, things often don't work that way. Natural logarithms turn these linear relationships, looking at absolute changes, into proportional relationships that use percentage changes. This is often a more informative and realistic way to look at things, and so economic models very frequently use natural logs. The nice thing about incorporating natural logs and also the polynomials that we'll look at in the next video is that we only need to do a little bit of manipulation of the data and don't actually need to learn any new regression technique. The regression works exactly the same, but the interpretation does change. Before moving on, it is important to make sure you have a solid understanding of the basics of logs. To get us started, let's think about two different price changes. First, we're going to change a price of a product from $1 to $2. And in the second, we are going to change a price of another product from $100 to $101. In both of these examples, we're changing the price by $1. If we were to use a linear model, it would assume that the relationship between price and quantity stays the same whether you're going from $1 to $2 or $100 to $101. In reality, consumers are probably going to view these price changes very differently. We can reframe these price changes as, in the first case, a 100% increase, and in the second case, we have a 1% increase. By using a log model that uses a percentage change interpretation, we can now view these two different changes in a totally different way. There are four different combinations of how we might incorporate natural logs into our models. The first is the level model. This is in many ways our baseline, where we have y equals beta naught plus beta 1 x plus epsilon. The level model does not have any logs in it. This is just our normal linear regression. In this model, if x increases by 1 unit, then y changes by beta 1 units. Next, we have the level log model. Here we have a regression of y on not x anymore, but the log of x. Log being short for natural logarithm. Here, if x increases by 1%, then y changes by beta 1 over 100 units. Let's break this down a little bit. Since x has the log on it, then x has the percentage change interpretation, but here y does not have a log, so that's still going to be changes in units. However, we need to convert from percents into not percents by dividing by 100 because 1% equals 0.01. Next, we have the log level model. In the log level model, we regress the log of y on x without a log. The interpretation here is that if x increases by 1 unit, y changes by beta 1 times 100%. This time, x does not have a log on it, so that's measured in units, and y has the log, meaning it's measured in percentages. Here we are converting from not percents on the x side over to percents on the y side, so we're going to need to multiply by 100. The final combination here is log-log. As you might expect, we have the log of y regressed on the log of x. In the log-log model, we have logs on both sides, so we have the interpretation that if x increases by 1%, then y changes by beta 1%. Here we don't need to do any multiplying or dividing by 100 because we have logs on both sides, so we have a percent change interpretation on both sides. Let's talk a little bit about why this works. Initially, it might seem like logs and percentages don't have anything to do with each other, but this all comes down to a mathematical property that the log of x plus delta minus the log of x is approximately delta over x. Here, delta is just a small change in the value of x. Remember from our discussion of elasticity that the change over the current value is the percentage change. And so logs generally do a good job approximating this as long as delta is small. The bigger delta is, the worse this approximation becomes, so just keep that in mind when you're using logs in regressions, that we want to mostly be limiting our interpretation to small changes. I've put on screen a table showing the approximation for percentage changes from 1 all the way up to 20. You can see here down at a 1% change, the difference in logs is very, very close to 1%. At 2%, it's again very close. But as the percentage change gets bigger, the approximation gets increasingly worse. By the time we get to 10%, we're down to an approximation that is about 9.5%. And by the time we get all the way down to 20%, we're down to about 18.2%. So you can see that the approximation does get worse. But if we stay in this area down here, we are going to be just fine. Another important point to keep in mind when working with logs in regressions is that the log of x is undefined for x less than or equal to 0. The log of x does not exist if x is 0 or negative. We're only allowed to put positive numbers into the natural log. If your variable x could have a negative or positive value, then we can't use natural logs. However, there is a workaround if we have an x that can be 0 or positive. Not negative, but 0 or positive. A good example of this is income. Income cannot be negative, but it can be 0 if a person does not work and has no other sources of income. Log of x is undefined for 0, but if we take the log of x plus 1, then we get around this problem. Now, if x is 0, then we have log of 1 instead of log of 0. Log of 1 is just 0. So that just keeps all of our 0 values as zeros, and everybody else just gets 1 added to their x. And for something like income, where the numbers tend to be in the tens of thousands, adding $1 to that income doesn't really matter. Let's do an example of logs in Excel. What we have here is a sample of communities in the Boston, Massachusetts area. For each of these communities, we have 3 variables. Price is the median price of homes in that area in dollars. NOx is the nitrogen oxide parts per million. This is basically a measure of how much air pollution there is in this community. Rooms is the average number of rooms in houses in that community. Before we run any regressions, we're going to need to create some log variables. I'm going to create the log price. In Excel, the function that we use to do natural logs is called ln. Then I'm just going to select the price and then copy that formula all the way down. I'm also going to do the log of NOx. We're going to do that the same way with ln, select NOx, and then carry that all the way down. The first regression that I'm going to run is going to be price on the log of NOx and rooms. Remember that in Excel, to run a regression, we always want to have our explanatory variables in a continuous block. So I'm going to select the NOx column and the rooms column, copy those, and then paste values over here on the right. Now I'm ready to run the regression. We'll go to the Data Analysis Toolpack, select Regression. For the Y range, we want the price. Select that whole column. For the X range, we are going to select our rooms and Knox variables. Let's take a look at these results. Remember that our dependent variable here is price with no log on it. So the relationship between price and rooms is a level-level relationship. Each room added to the house is going to add about $8,000 to the price. But the relationship between price and nitrogen oxide is level log. That means that we need to think about this as a 1% increase in nitrogen oxide will reduce housing prices by this coefficient divided by 100. So this means a 1% increase in pollution decreases housing prices by about $109. Always remember when we have to do that conversion. Next, we're going to go back to our data set and run one more regression. This time I'm going to change our dependent variable from price to the log of price. Let's take a look at our results. Looking at the relationship between rooms and price, we now have a log level relationship, meaning that we need to go from units for rooms over to percents for prices. So we need to take that room coefficient and multiply it by 100. This tells us an increase in the number of rooms by 1 will increase the housing prices by about 30%. Now looking at the relationship between housing prices and nitrogen oxide, they're now both in logs on both sides, so we have a log-log relationship, and we have the entire relationship expressed in percentages. So this tells us that a 1% increase in nitrogen oxide will decrease housing prices by about 0.7%. We do not have to do any kind of multiplying or dividing by 100 here because both sides are in percentages. We're now going to look at two different applications of natural logs to some concepts that we have talked about earlier in this course. Back when we learned about production and cost, we learned about the Cobb-Douglas production function. Cobb-Douglas production function, if you remember, looks like Q equals C k to the A L to the B. We previously did not have a C in there, but we're adding that now. This is just a constant coefficient here that multiplies our k to the A, L to the B. You can think about this as productivity. The bigger the C, the more production you're going to get. K and L are our capital and labor inputs. Q is our total output, and A and B are constants. Suppose that we wanted to estimate a Cobb-Douglas function with a regression. We can't do that because this function is not linear in terms. It does not look like a normal regression equation. However, we can use the properties of natural logarithms to transform the Cobb-Douglas function into something we can estimate using a regression. What we're going to do here is take the natural log of both sides of this equation. This is going to give us log of Q equals log of C k to the A L to the B. We're now going to apply our log rules to break this thing up. Remember that whenever we have terms multiplied inside the log, we can take the log of each of those and add those up. So we get log of C plus log of k to the A plus log of L to the B. We can then use another log rule to pull those exponents down. The log of C stays the same, and then we get A times log of K plus B times log of L. This equation right here is linear in terms, and other than the logs in there, looks like a pretty much normal regression equation. We have a dependent variable over here. We have a constant intercept term. This is essentially our beta naught. We have coefficients here to estimate, and then we have two explanatory variables. To estimate this, we just need to go into the data, take the log of Q, the log of K, the log of L, and run this regression. Once we run that regression, we're going to get an estimated equation that will look something like this. We'll have log of Q hat equals log of C hat plus A hat, log of K, plus B hat, log of L. Your regression output in Excel will give you these three things. We do have a slight problem though, because now we need to turn this back into a Cobb-Douglas function. To do that, we need to exponentiate both sides, which means we take e to the power of each side. So we're going to get e to the log of Q hat equals e to the entire thing here, log of C hat plus A hat log of K plus B hat log of L. Remember that exponentials and logs are inverses of each other, so anytime we have e and a log, it's going to cancel. So on the left-hand side, we just have Q hat, and on the right-hand side, we're going to use the rules for exponents to break this thing up. So we're going to get e to the log of C hat times e to the A hat log of K times e to the B hat log of L. We can also use our log rules here in reverse to move our A hats back inside the logs as exponents. So we're going to do that. Now all the e's and the logs are going to cancel. So what we're going to end up with is Q hat equals C hat times K to the A hat, L to the B hat. And now we've got things back into our original Cobb-Douglas function. So once we know A hat and B hat, which we get straight from the regression, we're just going to plug those things right in here. The only thing that you need to be really careful about is that our productivity term C hat is not the same as log of C hat from the regression. So in Excel, we're going to need to make sure to calculate C hat equals E to the log of C hat. So just take that log of C hat, plug it into the exponential function in Excel, and you'll get your C hat. The exponential function in Excel is equals exp, and then just put your number right in there. The last application we're going to do is elasticity. Remember, the definition of elasticity is the percent change in quantity divided by the percent change in price, or we can also do income, cross price, all those different elasticities. Since natural logs and regressions allow us to use a percentage change interpretation, this makes them perfect for estimating elasticities. Specifically, what we're going to need is a log-log model. Consider our example demand function from the previous set of videos, qxd equals beta naught plus beta 1 px plus beta 2 py plus beta 3 m. We can then take the log of each of these variables, so we get log of qxd equals beta naught plus beta 1 log of px plus beta 2 log of py plus beta 3 log of m. If we run this regression, beta 1 is our own price elasticity of demand. Beta 2 is a cross price elasticity of demand with respect to the price of y, and beta 3 is going to be our income elasticity of demand. The reason for this is that we now have a percentage change to a percentage change, which is the elasticity. Back over here in Excel, I've already calculated the logs of each of our variables, and so all we need to do here is go to the data analysis toolpack and run the regression. For the y range, we're going to use our log quantity, and for the x range, we are going to select our entire block of logged explanatory variables. Make sure labels is selected and click OK. The numbers that we get here in the coefficients are our estimated elasticities. So our estimated price elasticity of demand is negative 0.76, so it's inelastic. We've got our estimated cross-price elasticity 0.34, so we've got substitutes, and our income elasticity estimate 1.13. It's positive, so we have a normal good. And that is it for using natural logs in regressions. In the next video, we're going to look at one more nonlinear functional form, the polynomial.